All right. Today we want to talk about automated engineering, on how we can enable engineers to automate their daily work and how you can increase efficiency with that. And there we will have in today's episode a strong focus on FE automation. But this event is even more. It's about passion. What I realized over the years, if you are passionate for something, you are able to outperform the competition. And I'm passionate about all kind of action sports. So for example, snowboarding. And I'm passionate about being a dad. And for sure, I'm super passionate about automation in hardware engineering. And for that reason, I decided to do events like this, where we can show real engineering examples to help, on one hand, engineers to understand what can be achieved, but also on the other hand, business leaders to understand where are the low-hanging fruits and what can be automated with a short-term return of invest. And I'm more than happy to get support today by Tilman. And Tilman is also an auto enthusiast, but also an engineering enthusiast. And for this episode, we choose the rock climbing picture as a background picture. And Tilman, I want to ask you, what does rock climbing have in common with engineering in automation?
Yeah, thanks, Tobias. So first of all, as you can imagine, to be honest, it's also a little bit like an eye-catching. But for me as a rock climber, I see, basically some real parallel streams on these kind of things. Because, as I said, when it comes to climbing and having some specific problems on the rock, then it always comes to the point of, I would call it no return, where you have to focus and fight and be prepared and be right trained to get through the route and basically not fall in the end. And if I compare that with my experience out of the automotive industry and out of several development projects, it always comes also to that point where you basically reach areas where you have to be experienced, well prepared, basically trained on the right systems to get the job done in the end. And I would say, to compare that or to bring that together with automation and so on, that means to have the right people for the job also in development. So that becomes more and more tricky. Also, the timing becomes more and more tricky, and budget situations becomes more and more tricky in the projects we run in the moment. Means we have to find ways around it to be prepared for the situation in a project where it comes to situations where you have to be prepared. And in our case, and what our vision on that is that automation will solve that problem, because you can store basically knowledge in workflows and also bring more efficient way of development into these kind of project where it becomes tricky and where you have to be prepared. So that's basically the message behind being prepared and being also focused on the right things and on the right ways to develop in the future. That's the idea behind.
Awesome.
Exactly.
Cool. So I think that's the reason why we are all here. So who wants to see some awesome stuff here? So type in the comments yes without using the word yes. So, and while we wait for some of these comments, let me quickly share my screen. So 1 second. Here we go. So what I realized is that engineers facing more or less all the same challenges. So engineers spend too much time on repetitive tasks, such as creating PowerPoint reports, filling out Excel lists. And there are two problems with that. So one is, if this is not automated, a lot of errors can happening. but also it keeps the engineer away from doing really engineering work. So Tilman already mentioned things like that should be automated. We need to have this automated. But the problem with automation, on the other hand, is usually a CAD engineer, CE engineer can't automate the things because they don't have programming knowledge. And with that, there comes a third challenge. In engineering, we are used to always start from the scratch again. So it's pretty hard to reuse old data. For sure, we can use some old CAD data, modify it. But what I learned in almost 20 years of engineering, 80% of the project always needs to be redone. So, Tilman, are you facing similar challenges in your daily work?
Yes, of course. And basically, I would say every single day when it comes to development, you have to bring things together, and as you already mentioned, you have to start from scratch several times. And this is what you already said in the things we have to do in the current projects, or in projects for also in the future. More programming becomes important, and therefore it's basically the same challenge. You have to get the right people for the job, and this is always a little tricky situation, that you have basically on the one hand side the engineering guys, and on the other side the programmers, and you have to bring these both worlds together. And therefore, I would say a platform with a low code environment, what we want to show in the next few minutes, solves that problem, because you can have an easy access to these kind of let's say algorithmic development for getting automation into a current development phase. Maybe Tobias.
Big words. So I think everybody is now excited to see what you're talking about. So maybe can you show us a little bit how you solve these challenges in real life, in real engineering?
I can. Maybe first of all, I will show just the platform itself, just to maybe get a little rough understanding how to use low code for getting automation into a project. Hopefully my screen is visible.
Yeah, it works.
So maybe for the beginning, just to give a rough overview of the software itself, you have on the one hand side the canvas, which is basically the programming side, and on the other side the graphical environment. Means you can just do the programming in something like a low code environment. I will show what I mean with that. Just maybe a predefined node for creating geometry on the viewer on the other side. If you dare, maybe just put in a few parameters like radii and these things, and maybe in the end want to create an easy geometry out of that with, for example, using maybe different radii for just creating a circle or a ring. That would mean you can just type in these few parameters in here and create a geometry out of it. That's basically the initial situation. On the one hand side, you always have the input side, and on the other side of the nodes, you can just access the output, which is created by the component itself. And now, this is just an easy example, just for geometry creation. We will show something more complex in the next few minutes. But just to get an understanding, what is the current, or what is the initial way of designing in these kind of things, is that you have to be as parametric as possible. So you can basically easily change something in the beginning, just maybe change that to another value, and you will have directly response from the system in terms of graphics and so on. And if it comes then to for example, a CAE analysis, FE meshing and so on, you can just also use these geometry for example, meshing. I can maybe just just get one node on the canvas. Means you can, for example, use the common solvers like ANSA, like Hypermesh, and so on, and use that geometry later on for do the meshing and do later on steps in the workflow itself. So basically, this overall a combination out of different software environments. On the one hand side, the CAD situation. On the other side, the CAE stuff, and you also have these internal things of manipulating the input and output. As I said, we will show that in the next few minutes in a more complex way, but maybe as for the step now, maybe Tobias, you want to say a few words more?
Yeah, so to sum this up with my own words, and please Tilman correct me if I had a misunderstanding here. So, but that means you're not creating geometry meshes, simulations by clicking. It's more or less you're describing the process, and then you can reuse the process on your next project. Is this right?
Exactly, that's it. You're just creating the strategy how to build a component, how to validate a component, or whatever is necessary for the project. And for the next project, for the next development phase or whatever, for the next concept, you can just reuse that workflow, maybe with some specific changes. But overall, it's basically easy to use these kind of workflows and algorithms for the next few projects and so on. Yeah.
Cool. So, but what you showed, this might not solve a typical engineering problem. So you already highlighted it. There's more to show. So maybe you can show us a real life engineering project and how you automated stuff there and what kind of value it created at the end.
Yes, I can. So I have to share again. Give me a second. I stopped sharing. So I think most of you will know this environment, CATIA V5, just for designing a component. So that's the major idea behind with several other features, depends on the license you have. And a common way or a common situation in every project is basically you have designed something in the CAD in a CAD file, and you want to get the simulation guys or the CAE department to validate what you have done there and just check if the concept makes sense, or maybe wall thicknesses are in the right dimension and so on. All these kind of things which are interesting for a concept, you want to basically validate, and you want to also set up the best parameter set for all these things like rib height or wall thicknesses or material selection and. Basically, something like a trade-off in the end would be the best way of getting an analysis. But in most of the time, that the challenge is that you create a lot of concepts on the CAD side, and basically is that there's not enough resource in the CAE side to check all these concepts, and that makes it often too. I would say, not that easy to check what change makes the most sense for the development project. Means an automated process on these things would be a perfect fit for just a concept work, I would say. And that's where we are jumping in with automation. I will share the software again, the platform, and I just want to guide through a little what we have done in the project here, or in the workflow to explain what the different steps are. Means, first of all, you have to have a data ingress. Therefore, it is basically not important which kind of CAD system you use. For example, it could be the CATIA V5, or it could also be Siemens NX. It could be a step format. It could be Creo, whatever. First of all, the thing is you have to import it. And that's basically an easy thing here. You just have to select the right path for the CAD file. You can also use some PLM connectors and so on. Means this connection is basically just triggered by the saving process in the CAD system. after that ingress of the data, you have to run through all the different steps which are interesting for an proper validation of a component. Means you have to mesh it somehow. Therefore, as I already mentioned, you can use all the common meshing software, like, for example, Hypermesh. You can use also the ANSA mesher. You can use an internal mesher in the platform directly. And you have to tell the system at which point you want to apply some force, for example. In our case, this is just done by a color code, means for all the different hard points and for all the force apply points on the components itself. You just need to color the surfaces for connecting later on.
May I step in here, because I have a super important question. So that means you can easily, in the CAD environment, you design your part and then you have a specific color code. So it looks like in your case, it's green or some greenish color. And every surface I apply this greenish color to, there will be a load applied, for example. So correct.
For example, that would be one way you can do it. There are many other ways. It's just you have to give the system a trigger point how to detect the surfaces you want to overhand basically to the simulation. And in our case, it was the easiest way was just to use a color code. It could also be just putting the surfaces in the right container in CATIA. It could also be using just coordinates for example, hard points, and it will search for the right things in here. It could be a specific other component, means there maybe in the end there would be a bolt which is coming through these both things. If this is somewhere stored in the CAD environment, it could also be this one just for detecting the right surfaces. Is that what you meant?
Yes, exactly. That was what I wanted to understand. So can we do it somehow live? So modifying the geometry or whatever to see what's actually happening. I think that's what everybody's looking for.
No problem. I can do that. I changed just a little thing, but maybe just for explanation first. Later on, there comes the simulation. If I now do an update and start the workflow again, it will take a few minutes to run the simulation again. Maybe just to highlight that first. In the end, there's a viewer for getting some feedback from the system in terms of stiffness strength, in terms of maximum stress, and then if I now do the change in the CAD environment, I have to just update the data ingress. That means for that step, for example, I will just change an easy thing. Let me just see if there's something I can easily change. For example, I want to change the whole data here, or that could be just an easy one. Just run the update later. Maybe there could be something more interesting. Maybe I can cut the hole through somewhere else, which is also not that complicated. So maybe my design skills are not the part of the meeting in the moment, but that's just to get an easy understanding what we want to do here. So just maybe let me cut something through the component. So an easy change here. Maybe I can cut another hole through here also, that we can see a little more.
I think it's good enough. So
should be enough.
Principle is clear.
Principle is clear. I changed something, just cut the through holes more through the component, but yeah. So that's it basically. So geometry is updated, geometry is saved. You just have to hit the data ingress again. It took a few minutes to update, a few seconds to update.
So is the geometry already then updated now in the platform?
Give me a second. Took a minute. I have to wait for it. And so in the meantime, I can guide through the rest of it again and just show the other steps of the project itself, of the workflow itself. Okay. So, okay, the major thing is first step would be the data ingress, and the next thing then would be just to mesh the component itself. Means there's some meshing nodes below here where we have to select the right geometry and get the sorry, I'm a little confused now why it is not working. Let me just open it again. That's not a big thing here.
So this is really a live event.
That's
so how engineering projects are looking like. Sometimes everything goes fine. Sometimes adjustments are required.
That's it. So choosing the right component. And now we have to wait a second until the component appears.
So you save the part and now you try to import it, right?
Exactly, that's it. Yeah, I checked it several times before the meeting, but that's exactly the thing of a live session. We have to wait for the update now. I guess it will appear in the next few minutes. I don't think that there will be an issue, but let's wait for it. I will guide through, and later on we can look at the results.
Okay, so while waiting, that means you save the part in CATIA, you re-import it, and then the whole process runs through. What's here the added value for example, for the CAD engineer?
So the major thing behind is that every single change, as I already did in the CAD system, every single change will just create another version and another validation loop. And the thing behind is, if we want to check all these different concept steps, that would mean that every single concept has to be validated by a CAE guy out of the CAE department. And this took way too much time. So now it appears we have the hole in here, we have the changes in here. Now we have to wait for the meshing and so on. But this is now took time in the workflow. So I'm glad that it works finally. I think it was just the wrong path I selected. But yeah, fine. So basically, that's the major thing. All the different changes in the several components will create another simulation loop, and that causes way too much time lag, basically. And this is what we want to solve with automation. That every single CAD designer has the option to just check his design, his concept on his own, and that makes it way more efficient than the conventional way, where it took days or maybe weeks just to get the validated concept. In the meantime, there's basically nothing happening for the component, for the concept, and so on. And also for checking all these different little steps, it makes it also for the customer much more interesting to, or much more it creates much more information for the customer, which change does which reaction on the system itself. So that's I would say the major point of the or the major benefit of using a workflow like this.
Okay, so when you're showing a workflow like this here, then I assume you have to already use this workflow in several projects. So can you tell us a little bit what was then the impact based on maybe some rough KPIs on the project itself?
Yeah. So the major impact was, I would say, saving around about 25% on cut side, just about better utilization of the cut resources. I think that's the major case on the cut side, that the several resources are utilized much better, and you can just run different concepts and have not this waiting time. So on that side, it's around about 20 to 25%, which we saved on cut side. On the other hand, on the CAE side, just the validation guys, basically, on that side we was able to solve around about 35%, because we just reducing the sheer amount of CAE work later on. So all the huge CAE loops becoming, I would say, much smaller, or you can maybe just completely cancel one completely out of the development phase, and that just reduces the amount of work on the CAE side. Means cat side around about 20 to 25%, on the CAE side around about 35%, which we saved by using algorithmic development on these kind of validation processes.
Cool. I think that's a super great achievement. Okay, so it looks like the workflow is still running.
It is. So now we are in the solver run. Means it took a little time for just the meshing. Maybe I can highlight that first, just to show what is happening there. So in the beginning, as I said, it was just the data ingress. Then we have to run some meshing here. Means all the different geometries has to be meshed in the platform here. Also, as I already said, you can use the specific and the common measures for doing this job. Then the other thing was creating the connection. So all the different areas where we want to connect a feature to the component or applying force to it. You have to select the surfaces, and this is what is also optimized in here. Means the green color code is automatically chosen by the algorithm, and all the forces then applied by just using an Excel file. So it means all the load cases which are stored in here are basically given by, for example, an include file, but also maybe the possibility is also using just a huge Excel file with all the different load cases. I think in this one it was, let me just see, I think 20 load cases for the component itself. So a few different simulations which has to be run in here. The next one is just material selection. You can choose by using linear material. You can also use non-linear simulation and non-linear material, which is necessary then. Also for the CAE model work, if you want to use a non-linear simulation, then the model creation has to be a little different. This is just something you can easily change in the beginning of the workflow. Also, the simulation took a little longer than if you want to run a nonlinear simulation. It took, I would say, for this component around about an hour. I don't want to waste the time in the moment, so I just switched to linear, which makes it even faster. After the material selection, you have to build some connections, means the different hardpoints has to be connected with the component itself or the several components in the assembly. This is basically the common way, like in every CAE software it would be done. You can choose by using RBE3, RBE2 elements. You can also use bushing, spring elements. You can do a combination out of both, having RBE elements on the outer side, bushing element in the middle, whatever. So basically, this you are completely free to create here. And after the model creation, so the typical CAE model creation, you have to choose a solver in which you want to run it. So it could be Abacus, it could be the OptiStruct, it could be the internal solver. You can also use other software, basically like an LS-Dyna or an PEMCrash by just easy scripting connection. And then the validation process is automatically running, means that simulation took a few minutes then, as far as I know, it was 5 or close to 6 minutes, means it took a few minutes more. And then you can access again the viewer, so that the colored plot here with all the different load cases, which are just, you can just select by a drop down. You can change just looking at the stresses, looking also, and if you have the nonlinear simulation, you can also access the strain data, displacements, and. And what I would say is an interesting thing also, you can then create an optimized reporting. So for all these, for example, IDs for the several hardpoints, it could be interesting to see the several deflections. This is something you can automatically create and report from, also for the several stress plots for the deflections in the component itself. This is something you can automate and run a few nodes to create a PowerPoint output here. You can also.
That's super awesome. As everybody hates to create PowerPoint reports, or at least I hate it.
Yeah. At least on the CAE side, sometimes it took longer to create a PowerPoint report instead running just a simulation. So that sometimes that's a huge time thing, which is a time waste of creating just PowerPoints, and in the end, it's just for having a short look on it and then create the next concept. So if this is properly automated, I think that's something which is really, really helpful in the end. So just a few steps left, and then the simulation is done. After that, I can show the results.
Maybe while we are waiting, we can talk a little bit what's next, as we are already running almost out of time. So, as mentioned at the beginning, the idea is to host more of these sessions. So this will be one of the things. So once a month, or maybe even twice a month, we want to show here some kind of workflow, automated workflow. This time we choose the chassis part, but this could be also an electric engine, or even something totally different, but still following the same principles. We want to include maybe also some AI functions here, as AI everybody's talking about right now. And these are one things, but also there is something else planned from my end. I want to create some kind of a learning session to build this real engineering examples. So this will be a YouTube series every week. We will start next week with a simple workflow, and then every week we will continue to increase the functionalities of this workflow. And this is what you can expect next. After Tillman is showing now the results, I will share one slide where you can also scan our LinkedIn profiles. If you're not yet connected, feel free to connect with us, and also think about to switch on the notification so that you get all the updates we post on LinkedIn. But then, Tillman, show us the results.
Thanks, Tobias. Yeah, so finally, just in time, I would say, results of the components are done. So basically the simulation is ready, and you can just access now the several load cases. You can have a look on stiffness, strength, things like displacement, also on stress and strain later on if you run a nonlinear simulation. But, and this is something maybe in the last minute I can just show the reporting. It's just an easy example here. We have created a few pictures out of the component itself with some reporting behind. Means if there's an update in the component and in the simulation, it will directly create the same pictures again with some deflections for specific load cases. And this is something which could be easily manipulated in the end. So different views, direct look on hotspots, specific deflections on specific points, overall modal analysis, whatever. So this is something which is basically free to use and easy accessible tool for running reporting in the end. Yeah, basically that's it. A few minutes wasted in the beginning, but now finally this result is done.
One last question to the PowerPoint reporting. So that means you're using it a little bit with the whole component or system history. So just adding slides with every run, and then you can go through and see the history. Cool.
Exactly. You can just, for example, if you want to create just a single pass with a component name or whatever, you can just also integrate some merge text functions. Merge text functions by just creating an easy update with a counter or with a timestamp, whatever. So this could be again customized as you want.
Oh, cool. So then let me share my screen. So quickly for telling everybody how. I think you have to stop sharing your screen. Perfect. So everybody can easily scan our the QR codes, which will lead to our LinkedIn profiles. And what's super important, switch on the notifications. So just click on our profiles, hit this little bell, and put it to all to get all the updates we are sharing on LinkedIn. And say that I'm happy to get some feedback on the session. So if you liked it, also if you don't like it, happy to receive the feedback, what we can do better for the next time. And looking forward that everybody's joining again then in some weeks. So stay tuned, and thank you again, Tilman.
Yeah, thank you, Tobias.
Bye-bye.
Happy to see you in the next one. Bye.